Welcome back to Cloud on Air, the journey from big data to AI. My name is Dinesh Kulkarni. I'm a product manager in Google Cloud team, and I'm going to cover how you can simplify the machine learning lifecycle, starting from data exploration all the way to deployment of models. We have Googlers waiting to hear from you and answer any questions that you have. So please fire away your questions in the Q&A section. There's a lot of hype around machine learning, but the reality is that there is real tangible business benefit beyond the hype. For example, out of the hundreds of use cases that we see inside Google, here are 4 that illustrates how machine learning is changing the world internally for us and externally for our users. For search, machine learning is the #1 improvement reason. You might have heard in the press how AlphaGo managed to beat the human Go champion using deep learning. That happened because of all the research that was happening in deep learning to figure out how to handle a game that's much more complicated than chess. Likewise, Google Photos is able to recognize objects. For example, in this case, it's able to figure out that it's a glacier. And that makes a big difference in terms of the consumer experience, being able to tag different images appropriately. But beyond these, there is tangible benefit that is happening behind the scenes as well. For example, using deep learning, we've been able to achieve 40% reduction in cooling costs for our data centers. Now, data centers are complex environments. Each one is different. It's in a different environment. And so there's no simple formula to figure out, or even complex formula, to figure out what's the optimal cooling required at a particular point in time. But there is lots and lots of data available about the temperature at different points, about the humidity, external temperature, server workload, and so on. Based on all this data, we were able to train deep neural nets to figure out the optimal way of cooling data centers and save a lot of money in the process. So your business too can use machine learning in a very straightforward fashion. One of the benefits of the machine learning research that was done in Google is a library called TensorFlow. It's an open source library that operates on tensors and is able to express a wide range of machine learning algorithms. Google Cloud Machine Learning Engine, the machine learning engine or ML engine, is a product that is a hosted version of TensorFlow that can be run at scale. So we can bring thousands of machines to bear and GPUs and soon TPUs to solve your problem. There are already companies that are benefiting from it. For example, Airbus was able to solve a problem that had eluded them for decades. They had lots of satellite images where they needed to remove the cloud cover to understand the rest of the image properly. Now, in a satellite image, snow and cloud look deceptively similar, and it's not easy to tell which one is which. But by using TensorFlow and machine learning engine at scale and doing the training using deep learning networks, they were able to solve that problem in a way that human analysts just could not scale up to. Likewise, AXA was able to improve their ability to assess risk by using prediction based on structured data. There are many such examples where there is tangible business benefit to be had fairly easily by using advanced algorithms, by using machine learning at scale. But advanced algorithms is not all about machine learning. There's a lot more to machine learning. In fact, most of the effort goes into the overall life cycle of machine learning. Because a data scientist can use an off-the-shelf or an available algorithm easily, they don't have to worry about it as much. But they do have to worry about collecting enough data, understanding that data by exploring it, to figure out if there's cleaning needed or preparation needed, to join data from multiple sources. And then once they have the right data, doing feature engineering to figure out what is the most likely predictor. For example, for data center cooling, it was understanding the temperature at different locations and the server workload. It could be very different for your business. But there is a lot of effort that is involved specific to your business domain in understanding and working with data. Model development is another significant activity where you take the features that you have, the data that you have, train a model, then evaluate the model to understand if it meets your needs or not, and then understand why it's predicting the results that it is, so that you're sure that it's doing the right thing, even beyond the test data or evaluation data that you're using to understand the model. Then even after these two steps, once you have a good model that you like, there is a significant effort involved in operationalizing that model. You need to be able to deploy it for prediction, have an endpoint that can scale as your load goes up or down, and manage the model over its lifetime. So for example, when a new version is created, you want to make sure that that version is at least as good as the one that you have in production, and manage these models over time so you can understand how to improve them and get more benefits. So in order to really get the most out of machine learning, you need to master this life cycle. Here's a prototypical life cycle that shows some of the key steps in machine learning. Your specific example might be slightly different, but broadly speaking, you have steps going from exploration all the way to model deployment. So let's take a look at these in a demo. The example that I'm going to start with is using structured data for doing regression. In this case, we're going to take data about taxi rides taken in Chicago at different points in time, use the fare data that was collected, and figure out for a new ride what is likely to be the fare that the passenger will have to pay. So it's a fairly straightforward problem, but it illustrates the different parts rather nicely. Plus, it's a publicly available data set in BigQuery. BigQueries are petabyte scale data warehouse, which is serverless, which means you don't have to worry about setting up a cluster to run at a particular scale. You can just go from working with, say, a gigabyte of data to petabytes of data without even blinking. And we'll bring the resources to bear to provide you that capability. So that data is available for you to play with if you like. I'm going to use that here. Julia Child style, I've already pre-cooked this notebook, so we can quickly go through the different steps. So let's start with exploration. For exploration, I can look at run a query. Datalab, the tool that I'm using here, is based on Jupyter or IPython, which is a way of doing Python. We've added SQL capabilities to it in this fashion, where I can run a query and see the results and figure out what my data looks like. So these are the kinds of columns that I have in my data. There is information about trips, like when the trip started, trip ended, and so on. And then where the passenger was picked up, where the passenger was dropped off, and all that good stuff. Now, in order to use this data and understand it better, it's often helpful to have some visualizations. So let's scroll down to where we can look at the graphs that tell me a little bit more about this data instead of just looking at the table view. So what I'll do here is I'll say I want to explore this data. So I'll create the data set in the form of training and evaluation. This kind of split between training and evaluation is super critical. The reason for that is you don't want to contaminate your training with evaluation data or end up using the training data for evaluation. So keeping them clean and separate allows you to fairly evaluate your model. So we'll do that as a step here, which is create these two different ones, training and eval. Once I have these two data sets separated out of my set, in this case I've done 90-10 split, 90% going to training, 10% to evaluation. With that, I want to see what my data looks like. So I'm going to explore it in an overview form. Now, of course, you can write arbitrary SQL queries like I showed you up above and see the results in a table. But it's much more helpful to get an overview right away from a machine learning perspective. What are the kinds of things that matter to me? So let's look at the view that's generated. And again, this is done using the magic of BigQuery. So I didn't have to set up any database or figure out how to manage that cluster or anything. So in this case, what I see is these different columns. For each of these columns, I can see, let's go up and look at the details. So for each of these columns, I can look at what the total count is. So this is all on sample data. I took approximately 1,000 rows out of that. For this sample, I can see how many are missing. Looks like trip total is fairly well filled out, but the drop-off community area is not. It's got 20% missing values roughly. So I can look at it and decide whether my data is clean enough or if I need to exclude some rows. For example, I might not want rows that have missing pickup and drop-off information. That's not terribly useful. Whereas looks like the total fare is not a problem. It's always there. So with this, I can decide how to change the data, maybe fill in the missing values or exclude certain rows and so on. On the right-hand side, I can see the easily visible histograms, which tells me how many instances are in a particular bucket, so it's done the bucketization in order to understand how your data is distributed. You might have outlying values or anomalies that you may be interested in or not. Depending on that, you can choose to exclude them or keep them. And this is the kind of information that you can get just with a single command. So here, all you had to do was this %ml dataset explore, and it went against the dataset and gave you the information. So let's move to the next step. We've covered exploration. After that comes data preparation. For data preparation, I want to be able to do some cleanup. I want to be able to separate out the interesting values, even if they're bunched together. For example, here there is the timestamp information about when a particular write started or when it ended. But the timestamp itself is not terribly interesting in that form. What I want out of that is the day of the week. Was it a weekday? Was it a weekend? And if it was a particular day, what hour was it? Was it rush hour or not a rush hour? Depending on that, the same A to B ride might take very different amount of time and cost different amount of money. Or maybe it's a late night ride when a premium applies or a surcharge applies. Those are the kinds of things that I want to know. And that's what this preparation step will do. So here, for example, I'm taking out weekday from my timestamp. And similarly, getting rid of some of the values that are null and cleaning up my data. With that, I'm ready to go to the next step, which is pre-processing. Think of pre-processing simply as taking whatever data you have and turning it into numbers that your algorithm can understand. For each of these, for example, if I have a categorical column that says company ID, I might be interested in just encoding it in certain forms so that it's a number and it can be understood by my neural network. So that's the kind of work that analysis does in the first place, which is figuring out the range, figuring out the vocabulary, the total number of distinct values for a categorical column, and so on. With that, I'm ready to do the next step of pre-processing, which is transformation, which is actually computing those numeric values that I'm interested in based on, maybe I had 17 different values for taxi company, and I'm going to encode them as 1 through 17 or whatever encoding I've decided. The next step, once I have the pre-processing done, is to do training. In this case, we will actually see two different algorithms. First one is linear regression, and the second one, a neural network, a deep neural net. Now, both of these are available, readily usable. In this case, again, all I need is a single command, %ml train. By the way, % is a way in Jupyter of expressing what are called magic commands, and this one does the magic of training or analysis or transform. So in this case, I'm using a linear model. Even though I've run it before, what I'll do is I'll rerun it for the linear one, just so that you get a feel for what training looks like. And then we'll look at the results as well. Okay, so it started TensorBoard. Let's go and see what it's doing. So TensorBoard is a tool for monitoring a TensorFlow program. And it shows me loss. It shows me things as they are progressing. Now, in this case, the training happened really fast. But you can see that I can go through the loss and other curves. If I want, I can look at all the interesting data very easily. And all this is available at your fingertips from Datalab directly without you having to create any additional tools or install anything extra. Likewise, for the deep neural network, I won't redo the training. It's already done. But this is the model that I'm using, the deep neural network one. Again, the command is the same, just one simple command, mltrain. And the type of algorithm used is just a parameter. Now, for this one as well, I have the TensorBoard instance. I can see loss. This was run previously. Or I can even look at the graph. This is my deep neural network. And once you get really familiar with the details of the algorithm, it's often handy to look at those details. But let's get back to the life cycle again and see the next step. So once I have the training done, I have a model in hand. I don't know how good that model is. So the next step is to evaluate it. Remember, we had set aside 10% of data just for evaluation. Now that will be used for figuring out how well my model is doing. So let's look at that. It is interesting, as a side note, that evaluation is really nothing more than doing batch prediction followed by comparison. In case of batch prediction, you are taking a set of features and saying, hey, tell me what the predicted value, in this case for fair, is. And usually in batch prediction, I don't know the answer. That's why I'm asking the question. But here, I know the answer, and I'm just going to compare to see how well my model is doing. I use the same batch prediction capability with a single command, %% batch predict, and feed, tell it to use either linear or the deep neural network one. So linear in this case and deep neural network below. I've gone through both of those, done the predictions, and based on these predictions, I can look at the common metrics. The most commonly used metric is root mean square error, or RMSE. And I can see that for the linear algorithm, it's kind of bad. It is 7.83. That's high. But actually, it's not surprising. If you think about taxi rides, it's not a linear model. You can't just take distance and say it's proportional to distance. It's based on so many different things. Is it rush hour? Is it taking longer? What is the tip offered? What are the surcharges? What company I'm using? And so on. A very nonlinear problem. So not surprisingly, my deep neural network, which can handle very nonlinear cases, is able to do a lot better with RMSE of just 3.6. Now, this is one point where we can actually look at the value of throwing more data at it. So this whole training and everything that I showed was being done on sample data. In this case, I actually used 1% sample. I have 90 million rows, but I wanted some quick wins by looking at a model and saying, hey, does this look about right or not? So I used 1% of data, did all this work. Now, if I use all of my data, I have the opportunity to do a lot better. But in order to use all of my data, I'm likely not going to run it on a single VM like I did in case of my Datalab, which was running on a VM, using some data locally, quickly showing me the models. What I can do is essentially do training the same way with similar command. So let's go back to my sample data one, the one that we were looking at before. The train here was %% train command. Now in the other version where I'm using all 100% of data, it's essentially the same command with the extra -- cloud parameter tacked on. This is like a magic parameter. What it does is it says, hey, I need to do something at scale. So use your serverless capabilities in cloud and give me whatever number of workers I ask for. And based on that, ML engine will go and figure out how to acquire those machines and do the spin up TensorFlow on those machines and run the training. So this one is trained at scale in cloud with a -- cloud parameter. And now I can evaluate and see how my model is doing. It's the same metric, the same set of steps for doing batch prediction and comparing the results. But my root mean square error has gone down from 3.6 to 3.4, below 3.4. Now that might seem like a small improvement, but in a business problem, even small improvements lead to significant cost savings or revenue increases. So it's really important to have that capability at your fingertips, where you can quickly iterate, get a feel for your model, and then run training at scale the way we've done. The next interesting part to see is once I have this model and I'm happy with it, let's say I'm happy with my deep neural network, then I want to move on to the final step, which is I want to deploy this model. This model can be easily deployed with a simple command, just like in other cases for training and prediction. All I say is %% model deploy, and then Datalab will take the model, create a deployment using machine learning engine, and the machine learning engine will take care of predictions for you and handle scaling and all the good things that are needed in order to have a ready-to-go endpoint that can take an example or piece of data or row and return the results. In this case, take information about a ride, like start time and start location, end location, and predict the fare. So this is, in a nutshell, the entire life cycle. Let's quickly look at what the life cycle was. It was all the way from exploration to prediction. There is one part that I want to cover in addition to this life cycle, which is how to explain the results. For that, I'll use something a little simpler and colorful, which is a different problem set. In this case, instead of doing regression, I'm doing multi-class classification. Effectively, given a picture of a flower, my model is going to predict whether it's a daisy or a rose or a dandelion or some other kind of flower. And so it's a deep learning problem. I've already got a model and I've run the prediction against it, again, using the same command, %% predict. So same sort of simplicity that will let you do a whole step in a life cycle with a single command with a few parameters. Now in this case, it's good that I have predictions, but beyond that, I can also see how I can explain why those predictions are the way they are. So let's take a look at one of the common examples. Before that, let's look at the confusion matrix. Confusion matrix is an easy way of understanding how much confusion is there in the model between a correct result and some other possible result. For example, daisies are mostly predicted as daisies, not surprising, that's what you would expect. So I have a dominant diagonal, and then off diagonal are the confusions that the model has, where it says, oh no, the daisy is really a dandelion, or dandelion is daisy, and so on. But this doesn't tell me the whole story. I want to understand why it's doing that. It tells me the quantitative information, but it doesn't tell me qualitatively why it's doing that. So we added an extra capability called explain. It's again done in the same way with a single command, %% explain. It uses an open source package called Lime, which lets you understand how the particular model is predicting. Roughly speaking, what Lime does is it perturbs the images, figures out how the prediction is running on different perturbations of that image, and then figures out what part of the image is causing the prediction to be what it is. So in this case, for a daisy, you can see that this bright yellow outline on the image that I'm tracing out, this is the region of the image that caused my model to say that it's a daisy, which means it effectively did not use the rest of the image in order to predict. Now that may or may not be okay. It depends on your problem. But you can look at it, visually understand why your model is doing what it is. This is really important because in many cases you might be getting results that look good but for a completely wrong reason. The apocryphal story here goes something like this. A neural network given the task of distinguishing between dogs and wolves was achieving 100% accuracy. And that was on the evaluation data. But when they threw a real example at it, it failed. And they weren't able to understand why. And it turns out that their training data was biased. Training and evaluation, that data was biased. They had snow in all the wolf images, but not in dog images. So the neural network was simply detecting the presence of snow and saying, hey, it's a wolf. Sounds great until you see the explanation. And if you were to see this kind of explanation right away in front of you that said, look, it's looking at snow and saying it's a wolf, you would know, hey, that's not doing the right thing. I need to go back all the way to data collection and get more samples that have wolves without snow so that it doesn't key off of snow, or dogs with snow so that it's not confused based on snow. So that is sort of, even if you leave the apocryphal part of it out, that sort of illustrates the importance of understanding why certain things are happening. And in Datalab, we wanted to create an experience that not only covered the common case of going from exploration to model deployment, but also covered these kinds of interesting things in between, which is kind of the focus of running this at scale. Now, one part that I did not cover here is hyperparameter tuning. My model, so let's go back to my Chicago taxi example, and let's look at my training. When I set up something like a neural network, I have learning rate, I have some number of layers, number of steps, and so on. These are often called hyperparameters. You can tune them as a data scientist manually. You can pick different values, see which one gives you a better model. Maybe adding an extra layer or going from 7 layers to 10 layers gives you better results. Maybe not. This exploration can be extremely time consuming and taxing for a data scientist. Instead, what if you could just throw more compute resources at it and run 100 different or 1,000 different combinations of these hyperparameters to find the best possible model? Well, guess what? Machine learning engine lets you do that through hyperparameter tuning with a single call. Well, we won't get a chance to look at the code right now, but let's go back and see the life cycle all at a glance again. Okay, so this was roughly the life cycle that we saw, going from exploration to prediction. But in this case, I've added a first step of ingestion, data ingestion, because if you're going to use the serverless capabilities of BigQuery or machine learning engine, the first step is to bring your data to cloud. We have a set of products to enable that as well. And then I've added a few extra steps like managing jobs and models that are also supported by machine learning engine. So this whole set of products comes together, the suite comes together to support you in your task of experimenting with a model, building a model, deploying it, managing it in production, and understanding how to version the models and manage them over long periods of time as well, not just in order to get them running the first time. In addition to that, we saw that entire demo in Datalab, which lets you do these steps interactively, so you can go back and iterate at any point that you want. look at the results, look at the visualizations like the confusion matrix and a few other curves that we saw. RStudio has already previewed some support for TensorFlow, and that will likely evolve in future. And then you can take all these different steps, put them into a single pipeline to do continuous learning so you can keep improving your models and have a very systematic process in place for getting the most out of your machine learning project. The online prediction path itself can be richer. It's not just about your app sending an example or a row and getting back results. It could be a time series. For example, a time series of pressure sensor values or trades, financial trades that are being performed. And those can be ingested using PubSub and further processed using either Dataflow or Dataproc. Dataproc is our hosted version of Hadoop and Spark. And then machine learning engine can take over the prediction part of it. So with that, we can conclude by looking at the 4 main takeaways. Number 1, there's a lot of opportunity. We are at an inflection point where many business problems can now be solved using machine learning at scale. We can handle lots of data, lots of complex algorithms. We have tools and serverless capabilities for that. And in fact, that's how we boost productivity, by not requiring you to do the grunt work of setting up a database or having somebody in your company set up a database cluster or a machine learning cluster, but simply go and use whatever resources you need for whatever problem at whatever scale. On demand, just get those things ready. You don't even need to figure out how many are brought to bear. If your query takes a few seconds and requires 2,000 machines, that's a lot better than having 20 machines sitting there idle most of the time and then taking a long time for your query. Once you've got your model or your analysis done, then we have the ability to operationalize that. That's an important step to keep in mind, because data science is hard, but it's different from doing operationalization. And that is a different set of skills, different set of constraints and concerns. And those are covered by machine learning engine as well. And finally, all of this can be brought to bear in a very incremental fashion. For example, you could add recommendations to your app for the consumer, or you could improve your underwriting process in insurance, or improve your image detection capabilities. It does not have to be the hardest, the biggest problem right away. You can start small, build up expertise in-house and experience in your domain, and then graduate to harder and bigger problems as well. So that, in a sense, concludes this episode of Machine Learning Lifecycle. Thank you for joining us. Please stay tuned for the next episode.
Data center. It's kind of amazing. It's time to welcome back the AI track. Welcome. We've been discussing the clever and green data centers that Google uses to power all of the Google Cloud products that we've been talking about today.
Exactly. And one of the great things about a large company is that we have the actual physical space with interesting enough needs to play with. And these kinds of experiments are what really let developers hone the algorithms that we offer to others. So I think we should go ahead and introduce the next sessions. What do you think?
Outstanding, yes. We've got 3 more wonderful sessions along the same tracks that we have been looking at today. For the big data track, there's the Zen Guide to Data Preparation for Analytics, hosted by Eric Anderson.
For AI, Zach Stone and John Barris will take you through accelerated machine learning in the cloud. And in industry solutions, Jen Bennett is back, and she's discussing the new age of manufacturing.